All right, let's try another example. So here we have this function 2x squared over x squared minus 1. And we're going to kind of go through the process again. We're going to find the intervals of concavity, and then we're going to find any inflection points as well. All right, so we've actually looked at this example or this function before when we did the intervals of increase-decrease. So in that example, we actually went through the process of calculating and simplifying the first derivative. And what we saw there is we got f prime of x was equal to negative 4x over x squared minus 1 squared. Use some quotient rule. So we won't go through that again. We know, and why we mention that is we know for the intervals of concavity, we need the second derivative. So that's the first step in our work here, is we're going to calculate the second derivative. And so it took a little bit to get this first derivative. It's going to take even more work to get the second derivative. So we're just going to kind of use this result that we previously did to get our second derivative. And when we look at this, this is another fraction. There's x terms on both the top and the bottom. So we're going to do quotient rule again. So let's set this up. We're going to start. It's a fraction, so we're going to write it as a product. Top function times the bottom function. And then two copies, top function times the bottom function. In the first copy, we're going to apply the derivative to the first part. And in the second copy, we'll apply the derivative to the second part. And then we put a minus sign right there in the middle. And that's the numerator for our quotient rule. And then we make a nice big fraction. We take our original denominator, which, since we're differentiating f prime here, this is the one we're looking at, we take our original denominator, which was over here, and we square that. All right, so this is our quotient rule. Now we keep differentiating, and we have to kind of go through the work to simplify it. So let's finish differentiating here. And we're going to need some space. So derivative of negative 4x is negative 4. And then we have x squared minus 1 squared. Then we have a double negative here. Let's just clean that up as we go along. So that'll be plus 4x. And then what about the derivative here? Well, this is a chain rule. So we're going to have to do some chain rule here. So we bring down the 2. We keep our inner function the same. So x squared minus 1. Subtract 1 from the exponent, so it just becomes a power of 1. And then we take that inner function, the x squared minus 1, and we multiply by its derivative. So this right here, this is our chain rule that's going on to differentiate this x squared minus 1 squared. All right. And while we're at it, let's simplify the denominator. So there's not too much we can do just yet, but we have multiple exponents here, so multiply them together. So this is going to be x squared minus 1 raised to the power 4. All right, so now we keep differentiating and kind of simplify if you can as we go. So there's not too much here. We'll leave this kind of unmultiplied out. Let's just leave this alone. We could do a little bit over here, so that'll be 8x. And then we have x squared minus 1. And then what's this derivative of x squared minus 1? That's just 2x. Okay. Looking a little bit better. Still more we can do, though. So when we look at this, there's kind of two main pieces of our numerator. There's this negative 4x squared minus 1 squared, and then there's this second piece over here, which is this 8x times x squared minus 1 times 2x. And they're all kind of separated by this plus sign here. So we have the first part of our numerator, and then this entire big second part. And when we look at this, there's an x squared plus 1 right here, or x squared minus 1 right here. There's actually two of them. And then there's an x squared minus 1 over here, just one copy of that. And we have 4 copies of x squared minus 1 in the denominator. So we can actually do a little bit of canceling here. We can factor this out. So in the numerator, we can actually factor out an x squared minus 1. So if we look at the first piece here, what are we going to have left over? Well, we're only taking one of the x squared minus 1's out. So we're going to have a minus 4, and then we'll still have 1 there. So we'll have minus 4 times x squared minus 1. Then we have the plus sign, and we have 8x, and we're getting rid of this x squared minus 1, but we have this 2x. So let's fill that in. All right. And now we can cancel. So we have one copy here, and that can cancel out with one of the copies down there in the denominator. So we'll still have 3 copies left. And if we keep trying to simplify, let's distribute the negative 4. And then let's multiply these 8x and the 2x together. So we're going to have minus 4x squared plus 4 plus 16x squared all over x squared minus 1 raised to the power 3. All right. So a tiny bit more we can do. Clean up the numerator. We have these x squared terms. Let's combine them into 1. So we're going to have 12x squared plus 4 divided by x squared minus 1 cubed. All right. And that's about as good as we're going to get that. So it took a little bit of work, but we got our second derivative. And it's in a nice simplified form, too. That's what's going to be helpful. All right, so next we're going to have to figure out, well, where is this second derivative equal to 0, and where is it undefined? So that's going to be the next step. And let's see here, how much room are we going to need? We'll go over here. All right, so step 2. We want to know where is our second derivative equal to 0. And we found that the second derivative was 12x squared plus 4 over x squared minus 1 cubed. And when it's written as a kind of a single fraction like this, the nice thing about getting it into a single fraction is the only way a fraction can be 0 is if the numerator is 0. So that's what we're going to do. We're going to look at where the numerator is 0. All right, so let's take this 12x squared plus 4. We set that equal to 0, and there's no solution. Why? Well, for a few reasons. X squared is positive, so 12x squared is going to be positive, and if we're adding in 4, there's no way we can add 2 positive numbers and get 0. Another way to think of it is try the quadratic solution or quadratic formula. So if you have a x squared here plus a positive number, you're never going to take x squared and add in a positive number and get 0. It's like trying to add 2 positive numbers together. It's just not going to, you're never going to get 0 doing that if you're talking about real numbers. So there's no solution here. You try the quadratic formula, and what you would end up with if you use the quadratic formula, you would end up with a negative under the square root sign, and for real numbers, we can't have negatives under the square root sign. All right, so for our numerator, we don't get a solution, but we're also interested in where the second derivative is undefined. And the nice thing for fractions like this, the most common way for our fraction to be undefined is if we're trying to divide by 0. So that happens when we look at the denominator, and we're going to set the denominator equal to 0. So our second derivative equal to 0, just look at the numerator. Our second derivative undefined, look at the denominator. So we're going to set our denominator, which was, or is, x squared minus 1 cubed. We're going to set that equal to 0. And then from here, if we want to, we could do the cube root of both sides. Sure. That's going to cancel out the cube there. And when we do that, we get x squared minus 1 is equal to 0. And if we solve this, we're going to get x is equal to plus or minus 1. So, you can think of it as add 1 to the other side. So you have x squared is equal to 1. And then when you do the square root, whenever you apply the square root while you're solving, remember the plus or minus in front. So think x squared is equal to 1, and then you apply the square root. And whenever we apply the square root, put a plus minus in front. And that's how we're getting x is equal to plus or minus 1. So there's actually a couple places where the second derivative is undefined. All right, so that's important for our sign chart. So let's work on our sign chart here. So we're going to draw in our number line. This is a rational function, so it's defined for almost all real numbers, except where we divide by 0. Let's plot these two values that we found for our sign chart. We're interested in where our second derivative is positive or negative. So let's plot these two numbers. So -1 and +1. And that kind of splits our number line up into intervals. So we're going to do the interval from -infinity to -1. We'll do the interval from -1 to +1. And then we'll look at the interval from 1 to infinity. Okay. Then we just use our different factors here. So we have 12x squared plus 4. We have x squared minus 1 cubed. And then we'll see what that tells us about f double prime. And then ultimately what that tells us about function f. All right, so we have 3 intervals to check. And the way we're going to actually check them is with a test number. So that's step 4. Use a test number to kind of fill in the intervals here, whether they're positive or negative. So let's go through. For this interval from -infinity to -1, pick a test number in there. So -2 works. Plug -2 into this 12x squared plus 4 piece of our second derivative. And what do we get? We get 12 times +4. So when we square the -2, we get a +4. So that's 48. And then plus 4 is +62. We don't really care about the number, just that it's positive. Okay. Then we go down to this cubed term here, and we plug in -2. So we get -2 squared, which is +4. +4 minus 1 is +3. And then 3 cubed is +27. So positive. And since our second derivative is a fraction here, it's this term divided by this term. We have a positive number divided by a positive number, so the result is positive. Okay. So we just kind of repeat this then for the other intervals. So let's do a test number here for this interval from -1 to +1. 0 is always a good one to do. So 0 is inside there. Plug 0 into this first piece. We get 12 times 0, so 0 plus 4, +4. take 0, plug it into this other piece, see what we get. We get 0 minus 1, so negative 1. And if we cube negative 1, we get a negative. So when we cube a negative number, the result is going to be negative. So think of it as negative 1 times negative 1 times negative 1. So there's 2 copies of negative 1, which give us positive, but then we have a third copy that makes it negative again. So negative 1 cubed is negative. All right, so what does that mean for our second derivative? Well, we have a positive number divided by a negative number, so the result on that interval is going to be negative. All right, so then finally we go to the last interval, the interval from 1 to infinity. Pick a test number, anything in that interval. So 2 is a perfectly good number to use. And then we're just going to go through and plug it into each of these pieces. And what we're going to see is when we plug 2 in here, we're going to get, 12 times 4 plus 4. Another 48, 52? Did I say 62 before? I think I meant 52. And we don't care about that number. What am I doing here? We just care that it's positive. I think I said 62 for this when we were doing this one. We get 12 times 4, positive, plus 4, still positive. So the numbers, don't get hung up on the numbers. We're just interested in the sign. All right, what about take 2, take our test number, plug it into this other factor here. So we get 2 squared, which is 4. 4 minus 1 is 3. 3 cubed is 27. So positive. That's really all the main takeaway there. And so on this last interval, from 1 to infinity, we have a positive number divided by a positive number. So the result, our second derivative, is going to be positive on that interval. All right, so we've filled in all of the sign chart pieces that we need. Now we can actually figure out the intervals of our intervals of concavity. So when our second derivative is positive, that means our original function is concave up. And when our second derivative is negative, it means we're concave down. So we've gone through and we've identified, well, on this interval here, our function is concave up. On this interval here, our function's concave down. And then this interval, we're back to concave up again. All right, so we've found our intervals of concavity. Let's just write them out. So f is concave up on the interval from minus infinity to negative 1, and on the interval from 1 to infinity. And f, the original function, is concave down on that interval from negative 1 to positive 1. So we found the intervals of concavity here for this function. For this function, 2x squared over x squared minus 1. And we did that using our second derivative. All right, so inflection points. What are the inflection points for this? Well, we actually found our possible inflection numbers right here. This is where we kind of split things up on our number line. Those were the x values that we used. These are the possible inflection numbers here. We might have a inflection point at those. So this is step 5, inflection numbers. So we found, let's write out our possible inflection numbers. What did we find when we were doing our sign chart? Well, we found x equal to negative 1 and x equal to positive 1. And now we have to go through those kind of extra conditions. We have to check both of them. So what are those extra conditions for it to be an actual inflection number? Well, we need it to be in the domain of f, and there has to be a change in concavity. Okay. So our function has to change concavity. Let's look at that change in concavity. Let's look at negative 1. Let's go back to our sign chart here. And what we're seeing, where's negative 1? Right here. And on the left side of -1, our graph is concave up. On the right side, it's concave down. So it actually does look like there's a change in concavity at x equals -1. So we go from concave up on one side to concave down on the other side. What about +1? What's going on at the other one? Well, there we're doing concave down to concave up. Yeah, that's a change. So it looks like on one side we're concave down, on the other side our graph is concave up. That looks like a change to me. What about the domain of our function? Well, let's take -1 and just try plugging it into this original function. And when we do that, we get 2 times -1 squared on the top. So that's just 2. And then we get -1 squared minus 1 on the bottom. But -1 squared is +1. And +1 minus 1 is 0. So if we try to plug -1 into this function here, we get division by 0. The function's undefined. So no, -1 is not in the domain of our original function because division by 0. What about x equal to +1? What's going on there? Well, try plugging +1 in. We get 2 on the top, and we run into the same problem. We get 1 squared minus 1. We get 1 minus 1. We get division by 0. So x equals 1, if we try plugging it into this original function, gives us division by 0. So no, it's not in the domain. So this example might be a little tricky. Yeah, we're seeing a change in concavity, but those x values aren't actually in the domain of our function. So we actually do not have any inflection points. So these are not inflection numbers. The only way it can be an inflection number is if both of these conditions are met. And since this one didn't work, they're not inflection numbers. And what does that mean really in terms of what we're interested in? There's no inflection points. So this graph does not have any inflection points. So we found our intervals of concavity. There they are. But no inflection points. And that's because, well, these x values that we found, yeah, there is a change in concavity going from one side to the other side, but the function is not actually defined at those x values. All right, so that'll do it for our discussion of intervals of concavity and inflection points. And really the techniques here really rely on, or are very similar to what we did for the intervals of increase-decrease. So you just want to keep that in mind as we're kind of a concluding thought here. Gone through a bunch of examples, but let's just kind of just circle back to this. We've seen how to find the intervals of concavity, and really this is the same steps that we were doing for intervals of increase-decrease. The only difference is for increase-decrease, it was our first derivative, f prime. For concave up, concave down, we're using our second derivative. All right. So in the next lesson, we're going to see how to classify local maxes and local mins. So we'll see how to classify our critical numbers. And it's going to involve first and second derivatives. So we'll see you there. Bye-bye.